Paul, you want to share your screen? Welcome.
Sure. Okay, I hope everybody sees the screen now. It's working, thank you. So first of all, I want to thank John, Colorado State and the Center for Risk-Based Community Resilience Planning for giving me the opportunity to offer this seminar. It may be one of the largest professional audiences that I've had, you know, if you consider colleagues and graduate students. So I'm very, very honored to be here and grateful. So the title that I gave to the seminar is Regional Level Approach to Resilience Assessment. Some of you may have heard me talking about similar topics in other seminars. But today I want to focus on three particular themes across the topics that I will cover. The first one is regional analysis, right? So I see a lot of faces here of people who have been trained in structural engineering like myself. And one of the things that I want to consider is what changes when we go from the analysis of an individual structure to the analysis of a site. What things do we need to rethink? The second theme will be the concept of surrogate models. We all use surrogate models constantly, and I see that in my students, at some point, this becomes sort of routine, and this may happen in a way that is not really deliberate. I think that every time we use a surrogate model, we have to be sure that it preserves everything that matters and disregards everything else. I included this quote. I cannot really attribute it to anybody. I don't know the original author, but I think it really captures the essence that I want to convey. Engineering is the art of accounting for what matters and disregarding the rest. And the third theme will be this triple trade-off that I think we have always to do between our desire to have very accurate mechanical model, our desire to capture uncertainty and probabilistic aspects, and the need to keep the computational costs feasible. It's always very difficult to balance these three requirements, and this will be a recurring theme in what I present today. You see that these three themes are clearly connected. When you study an entire region, you need even more surrogate models, and you need even more to do this trade-off. However, now I've also taken some administrative duties at Lehigh. So before starting, I need to give a pitch. I see some students in the audience, so I will dedicate a couple of minutes just to talk about the institution. The institution is a little over 150 years old, which for this part of the country, I guess, means old. We have 5 colleges and about 7,000 students, 500 faculty. We were in the middle of a large expansion before COVID hit. Now that is on pause, but we expect to resume the expansion soon. The campus is beautiful. That's one of the things that everybody agrees upon, one of the few things everybody agrees upon. And it's beautiful in every season. We are located pretty much between New York and Philadelphia. I think that this map is a little bit misleading. We can actually drive to Philadelphia in less than 1 hour, and we can be at the Holland Tunnel to access Manhattan in a little over 1 hour. The area where we are is about 800,000 people, split into 3 different major cities. And if that's not enough, we have easy access to major metropolitan areas. Our department in particular has a good history, and we have been doing well in the rankings. This is one of the international rankings that people check. And in the last 5-6 years, we've always been among the top universities in the United States for this ranking. We're not doing as well in the US News and World Report. In this case, we're number 33, but I think that the general message is that we are among the good schools where students can come and study. This is built upon more than a century of tradition, specifically in structural engineering. the Fritz lab was established in 1909. This press that you see in the figure on the right with Mr. Fritz is still operational. And for this reason, the place has been made a landmark of civil engineering by the American Society of Civil Engineers. In the 60s, 70s, they expanded and basically doubled Fritz Lab and brought here what is still the largest press in an academic institution. I think that the second largest in America. It's a 5 million pound machine used constantly for industrial testing and research. My office, the office I'm talking to you from, is about here. So if at any point you hear a very loud noise, don't be worried. They're just breaking a bridge pier next door. After that, they couldn't really bring in a bigger press than that one. So they established Atlas. At Atlas, the idea is that they built a very big rigid box and with regular fixtures. And what they do is building structures there, attaching an actuators from the structure to one of the fixtures or more than one of the fixtures of the rigid wall, and then testing entire structure. So the idea is that you build a testing machine on top of the structure. I know that John and several other of you have already used Atlas, but it's really a one-of-a-kind facility. And one of the things we're particularly proud of is that we are a member of the NERI network. We're one of the 8 laboratories of the NERI network. We are the strong wall lab. Now, obviously, all this experimental research has to be backed up by analytical and numerical research, which is most of what I do. And the flagship project in this area is what we call the PRAISys Project, which stands for Probabilistic Resilience Assessment of Interdependent Systems. It's a project that was funded by the National Science Foundation. It involved 58 researchers. It was a major operation, and the general spirit was to try to predict community resilience, evaluate costs and benefits of different alternatives, and plan accordingly, focusing on the transportation network, power network, and communication network. The project was completed after 5 years last October, but obviously we're continuing to work basically in the same spirit and the same areas. So we're talking about resilience, and I like to use this quote that says, it's not about how hard you can get hit, it's about how hard you can get hit and keep moving forward. And some of you may recognize that this is a quote from one of the most famous Pennsylvanians in history, Mr. Rocky Balboa from Philadelphia. Now, if you want a more formal definition, I like to use this one from the White House that says resilience means the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions. In engineering terms, this doesn't come from the White House, but I personally like to think of it in this way. Structural safety and reliability traditionally focused on hazard and damage probability. If you talk about risk, it means that you're including in the analysis also a study of the consequences of potential failure. And from my point of view, what resilience really adds to all of this is an explicit attention also to the recovery phase. And here I know that I'm preaching to the choir, and I don't need to explain why the recovery phase is so important. Countless studies show that the losses, social and financial losses in the long-term disaster recovery are often larger than the immediate losses of extreme events. For this reason, to address this problem, the PRAISys project had to span multiple hazards. Initially, we worked on earthquakes and hurricanes, and the results that I will show today refer to these two perils. But now we're studying also floods and wildfires. players. It is multi-sector. As I said, we work on transportation, electricity, and communication systems and various components of these systems. And we just started working on water and wastewater systems. It is multi-scale, and I will talk a little bit about the range of scales that we have to deal with later on. And it is multidisciplinary. We really had a team spanning various areas of engineering and way beyond that, just like the center of excellence. The PRAISys platform that we used as a sort of hub where we tried to make a good part of our research convey is including 5 modules: the hazard modeling, the damage assessment, the decision and planning, that is a decision and planning simulation, right? So we try to predict how the humans will react and try to plan for recovery after the disaster. And then the recovery simulation, which may lead to results that are very different from the initial plan. We'll take into account the initial plan, but then we'll develop a more realistic outcome. And finally, resilience forecast, assessment of some metrics. The way in which this is intended to be used is for pre-event decisions, right? So the idea is that you use this, you simulate post-event decisions, you evaluate how the model, how the outcomes can change based on possible mitigation actions, and then you make a call on how to best allocate resources. Last week at the workshop, we have seen several other platforms addressing very similar problems, much better established than ours. In our case, we try to put particular emphasis on uncertainty quantification and propagation and on interdependencies and specific relationships. And we also like to study the intersection of these two that we call probabilistic interdependencies. Now, I will talk quite a bit about uncertainties, at least in the first part of the talk. I will not talk very much about interdependencies today, but I just wanted to mention that in the platform, we addressed in different way 11 classes of relationships, dependencies, and interdependencies. And we tried to classify all of those that we thought were meaningful. And we put some of our thoughts and models in a couple of publications. In particular, there is this Objective Resilience Manual of Practice of ASE that will probably be published in a few months. And we wrote the chapter on interdependency. So most of our thoughts and the literature review can be found there. So what I want to do today is talk about a few of these modules and some of the research that we have done that belongs to a couple of these modules. So for the hazard modeling module, I want to talk about hazard quantization. That is in itself a line of research that I've been playing with for a few years with some great colleagues. And this again is related with the concept of going from a site-specific analysis to a regional analysis. We know that we have hazard maps. We have hazard maps for earthquakes, like those that I'm presenting here. We have flood maps. We have similar things for hurricanes. They are a great design tool, and they provide information in the form of an actual map or in the form of a hazard curve for each specific site of interest. Now, the problem is that when we're studying an entire region, hazard maps are not enough, because we don't want to know just the probability of reaching a certain intensity measure at one location A or at another location B. We also want to know the probability of reaching that level at both locations simultaneously. Because when you're studying a network or a system, the effect of having compound failures is always very much relevant. So people have addressed this problem in different ways. Some colleagues did great work on analytical or numerical ways to try to compute directly this correlation, and there is great work out there. Some of the limits is that when you address directly the correlation, they often end up having to make simplifications or assumptions that can restrict a little bit the range of application of each methodology. What I prefer is instead to work in a different line of research that is generally classified as hazard consistent scenario selection. So here's the idea, is to select a suite of scenario events represented by a map of the intensity measure at in the region of interest, and select these scenarios in a way that in the ensemble, they match the probability of exceedance at the grid of location or at the location of the structures that we want to study. Now, because of my background, I started thinking of this really as a problem of random functions. An intensity measure map is essentially a two-dimensional random field, non-Gaussian and non-homogeneous. So if we interpret it in this way, what we really want to do is capture the hazard that in terms of random fields would be the marginal distribution at every location, and capture the correlation, that is the relationship between the value of the intensity measure at the various locations. Now, the hazard consistent scenario selection studies try basically to match the marginal distribution, right? They enforce the matching of the marginal distribution through the matching of the hazard. And then the correlation is hopefully provided by the fact that we're using real intensity measure maps, and so they will be somehow correlated. Now, I was not entirely satisfied with this concept, because the reason why we're doing all this is that we want to capture that correlation. So I wanted to find an approach that is a little bit more deliberate in addressing this correlation and not just match it as a byproduct. So the idea that we followed is this concept of hazard quantization. And I like to present it first in this sort of pictorial representation. Let's imagine that this here is the sample space of all the possible scenarios that can affect a region, right? So each dot is a scenario event in this space. We have some events that are a little bit more frequent, and then we have some events in the fringes that are a little bit unusual. Ideally, what we would like to do is test all of these scenarios. Unfortunately, PRAISys, and to the best of my knowledge, also all the other simulators of resilience are very, very expensive. So more than this, we really can do something like this. We have a very small set of samples that we can actually use. So the question is, how do we represent the sample space with such a small set of samples? Well, a first step is that perhaps we can measure the area that each one of them should represent, the region that each one of them should represent, and use this as a sort of probabilistic weight to combine them. But an even better way to do this is to try to engineer the way in which we do the sampling so that the samples are better spread. And this is an idea that in the random functions literature was introduced in 2002 under the name of functional quantization. And these researchers not only introduced the concept, but they also proposed a methodology to try to do this process. But it applied to a very specific class of random functions, and unfortunately it didn't work for hazards. So we had to take this idea and generalize it to multidimensional, non-homogeneous, and non-Gaussian fields. The basic idea is this one. You take a random function f, and you approximate it with another function, fn, and the approximating function can be represented just by a set of samples, the hazard scenarios that we actually want to study, and the set of probabilities, one for each of them, that serve as weight to measure their importance. So if this is, again, the sample space of all possible events that can hit the region, this is one, let's say, earthquake, and that earthquake is associated with a certain, let's say, PGA map over the region. Another earthquake will generate a different PGA map, and so on and so forth. The approximation that we're doing is to take the same sample space, partition it into a series of regions, and then say that all the events that belong to the same area, to the same region, are actually mapped to the same sample function, right? So this is the approximation that we introduce. And it's good because it allows us eventually to just use a relatively small number of scenario events and associated probabilities. So this is where we want to get. So if we want to formulate this in a slightly more formal way, we say that given the desired probabilistic characteristics of the random function to be represented and the small to moderate number of scenarios that eventually we want, that you can simply calculate as the time available over the time of a single run, we have to find an optimal quantizer, which means an optimal partition of the sample space, an optimal set of representative functions, and the probability associated with each subset in a way that is applicable to random fields that have the shape of, they have the characteristics of intensity measure maps. What does optimal mean? We'll see in a minute. The trick, I'm not going through all the details of the methodology, but the basic idea is that the methodology is entirely formulated in this space at the top that I represented with these squares with rounded corners. That is the sample space of all possible hazard events. This is a terrible space to deal with because we know very little about it. It's very abstract, and we can do very few operations up here. So the basic idea is to map this space to another space, that is the space of square integrable functions, that is basically the space of intensity measure maps, and do all the operations down here. Do the partitioning here, do the selection of the functions here, do the weighting, the calculations of the weights down here, always remembering that the sample, the random function, allows us to go back and forth from one space to the other. So we still have to answer those three questions. How do we obtain the optimal partition? How do we compute the quanta? And how do we compute the probability for each one of them? And thankfully, the answer to all three questions is one. It's that we need to do a centroidal Voronoi tessellation of this infinite dimensional space. To explain this, I like to start again with a simple two-dimensional Euclidean space. So I think that most of you are already familiar with the concept of Voronoi tessellation. If you have a space and you have some generating points, these red dots, the Voronoi tessellation is made in such a way that all the points in a certain region are closer to their generating point than to any other generating point. So basically, all we need to do is take every pair of generating points, cut in the middle, and basically those lines will generate the partition. For each one of these regions, we can also compute the centroid. And in general, the centroids, these black circles, do not coincide with the generating points. A centroidal Voronoi tessellation is a special case of Voronoi tessellation where the centroids and the generating points coincide. And this has a lot of beautiful mathematical properties, including the fact that it minimizes this particular functional called distortion. And again, I'm not going to discuss the details, but I want to just show that here we're basically minimizing this norm, that is the discrepancy between the actual function that we wanted to capture, right? So the actual function that goes from the event to an intensity measure map, and the FIs that are our quanta, the approximation. So we're not minimizing the discrepancy in the hazard or in the correlation. We're really minimizing the discrepancy in general of the first and second order moments. And so we make the two functions converge. So we just have to do a centroidal Voronoi tessellation with the issue that in theory we have to do it in an infinite dimensional space that connects an event to a PGA map or a wind velocity map, etc. There is an algorithm to do this that we adjusted a little bit. It's extremely similar, we eventually learned, to the k-means algorithm. Basically, all the first 80% is the k-means algorithm, and it changes only at the end in the selection of the function. And these are some examples of its application. This is just a demonstration. Here we took a region, very unlucky region, with two huge faults, and we randomized the location, the magnitude, and the depth of the hypocenter for an earthquake. And then we studied how the intensity measure maps can occur in this region, given that an earthquake happens. This is one sample. Here we were not using residuals, so local variability. This is just a smooth attenuation function. And this is one quantum. When the quantizer size is 50, you see that they're not identical, but there are similarities. And this is how well we're doing in terms of our ability to capture the marginal distribution, for instance, the hazard, basically. For instance, in terms of spectral acceleration at 0.1 second for this particular acceleration. You see that these two curves are extremely similar. Here, when I say exact, this is not really exact because we didn't have an analytical formulation, but this is the result of 500,000 samples. And this is what we can get with just 50 samples. This is an even better way to look at this. The thick colored lines are the reference solution. The thin black lines are the results of our quantization, and you see that we capture very well the region. Now, this is in the middle of the distribution at 0.4 G. But even if you look at the tails, like 0.1 G, you see that we're doing very well. And if we go through with 0.2 G, 3, 4, the methodology captures very well the reference at the lower and upper tails. And even if we just use 50 quanta, the calculation is pretty good. Now, that was the easy part, right? Capture the hazard. But even in capturing the autocorrelation, we're doing very well. This is the comparison between the reference and our result. I put too many R's in autocorrelation, I guess. And the discrepancy is in the order of 10 to the minus 4 when our values are in the order of 10 to the minus 1. So we're capturing very well the hazard and the correlation. We try to do this also for a more realistic case where we try to include all the possible features of the earthquake. And we compare this to what I consider to be the two state-of-the-art techniques to address this problem, k-means clustering and optimization-based probabilistic scenarios. And the outcome is that in terms of the hazard curve, all three methodologies do pretty much well enough. You see that all three curves here are very, very close. In terms, if you want to measure the error, also here, the errors of the three methodologies are very similar. Ours is hazard quantization and the other two. And in particular, when we look at the error in the autocorrelation, we're doing very well. And the error is consistently lower than these other two. So we think that this is a good alternative to the two best and most popular techniques that are out there. Now, a couple of things that we have been playing with most recently. The first one is what we call hybrid hazard quantization. And the idea is that if you propose to someone here in Pennsylvania to do a hurricane study, they will never accept any analysis that doesn't include Sandy as one of the potential scenarios. So there are some, there is the desire to have some historical events as part of the portfolio that you eventually study. And also this helps us in addressing one of the limits of hazard quantization, that is that we're not doing very well in capturing some very local variability. Introducing also some historical maps helps a lot in that sense. But at the same time, we didn't want to just do our quantization and then throw in some additional scenarios. We wanted our hazard quantization to select scenarios knowing that eventually there was going to be also a set of additional predetermined scenarios. So this is what we did in a two-dimensional conceptual example. The three black dots are static. They are the predetermined scenarios that have to be part of the final set. And as you can see, all the other dots basically adjust around them and build a quantization that results in an optimal partition while keeping those initial scenarios. Now, we did this for hurricanes. I don't have time to show all the results, but it works. To do that, we also had to build an in-house full-featured hurricane simulator. This was a major effort. I think it is really state-of-the-art. We have the genesis model, the track propagation, the track termination, the entire wind field, including features over water and over land, which I think is one of the original features. One of my students and then postdocs really did the trick developing this thing. Then he was snatched in the middle of a postdoc by an hedge fund that is investing into cut bond, and went to him, showed him a check, and the next day he was gone. So the reason why we really wanted the simulator is that we are combining it with NOAA's storm surge simulator, and we're trying to do what we call multivariate hazard quantization. So we're combining wind related intensity measures like sustained wind speed with a storm surge model. And so we will have samples that are a pair of wind intensity maps and flood intensity maps, and we're doing a quantization on both. 2 weeks ago, we completed the proof that the optimality transfers very elegantly also to the case of multivariate functions. And now we are in the process of combining these two with some help from NOAA to test it for multi-hazard analysis. Finally, where all this is going, one of the things that I never liked about this is the fact that the problem consists in having an input that is our intensity measure map, given by the quanta, optimal. We have a proof of optimality of this, and then we do a resilience analysis, and then we get as output our system resilience. Now the question is, does optimality of the input guarantee optimality of the output? And the answer is no, unfortunately. What we would really like to have is optimality of the output, but we can only prove optimality in the input representation. So to address this, what we're doing is something called multi-stage hazard quantization. It has a side benefit of helping us investigate better the fringe cases and capture also small distance fluctuations. It enormously accelerates the quantization process that becomes very important when you have multiple hazards. And most importantly, it compromises a little bit the optimality of the input to help us get an even better representation of the output. This is a work in progress. We have some analytical results, but we don't have numerical results yet for this. Now, I have some time, so I will start talking about a second module. I will go very briefly about this. That is our damage assessment module. And for this one, what we do is what we call advanced fragilities. You know, all of us, speaking of surrogate models, know that when studying entire regions, a fragility curve or a family of fragility curves is probably the best way to go, because it's very efficient and allows us to capture probability in the failure. Unfortunately, for a lot of structures, we still do not have fragility curves, or we have some very rudimentary first attempt at a fragility curve. So a lot of what my team has been doing in the last few years was building these curves for various classes of structures, from transmission towers, telecommunication towers, conductor cables, bridges, elements of substations, electrical substations, etc. And in all these cases, we had to go across multiple scales. Here, for instance, for the case of power networks, we have studies on individual bolts and the mechanics of bolts and joint connections, how these influence the behavior and potential buckling of angle members that are those that normally determine the failure of transmission towers. And then how towers interact with the conductors, and the conductors themselves can actually fail. And then the failure of a tower or of a conductor can lead to the failure of the entire transmission line, which may or may not be a problem for the network. So we often have to span, in this case, 8 orders of magnitude of distance, from millimeters to hundreds of kilometers. And we have to branch different sciences in some sense, from continuum mechanics to system analysis. At every step, again, the recurring theme of understanding what you really have to capture and what you can leave behind is crucial to make sure that you get to a final result that makes some sense. For instance, we did a very long study on the mechanic of joints in these particular towers that, to my surprise, was a little bit understudied. We first had to understand all the phases that these bolts undergo, these joints undergo under cyclic loading. And then we started with the experimental results that were available, unfortunately, only for static cases. But based on those, we built and calibrated a high-resolution, 3-dimensional model of the entire joint and each one of its components. Out of that, we built then an analytical model of the cyclic behavior. And then out of the analytical model, we coded an OpenSeas element, actually an OpenSeas material, I should say, that is now published and available for others to use as part of their models. And each time we had to go back one step and use the results of the previous step for validation. But the outcome is that now we have an extremely efficient element that can model these type of joints in an OpenSeas model. These are just some examples that show the comparison between our OpenSea element with the full scale, high resolution Greek elements model. And you see that it's doing pretty well. And as I said, the code is public. Other examples of work that we had to do specifically to build these fragilities for towers was go against the traditional approach of studying just tip displacements, because they are a very good metric of the global behavior, but the failure of these towers is normally driven by local buckling. And so we had to do element-based analysis to capture this. We had to change the way in which we were modeling the interaction between the towers and the cables, because a naive approach would require the simulation of a random field with hundreds of components, which is invisible in this type of cases. So we instead found a way to reduce everything to a random field with 21 components and validate it and show that it's extremely accurate. We had to do something similar, for instance, to model those joints, because we showed that if we had to do an analysis with the joint models for every joint in our truss, the computational time would be 12 hours, even with those efficient models. And what we wanted to do was a much simpler model that would take only 6 minutes. Now, what we noticed is that the behavior of the complex model and of the simple model can actually be obtained for each node and for each component of each tower simply by scaling, finding a specific scaling factor. So what we could do is run a couple hundred complex analyses and pair them with a couple hundred simple analyses with the same load, find for each joint the corresponding scaling factors, and then run millions of analyses with the simple model. Again, we go to the need, back to the need of trade-offs. And here, I think this graph is very important. It shows At the end of the day, what we want to find is the probability of failure. And here we need a trade-off between having a very accurate but slow computational model in terms of mechanics that allows us to run a relatively small number of probabilistic samples, or run more samples but with a simpler model using some clever scaling as we did. And here you see that the simple model not only is faster, but for a fixed amount of computational time in terms of which affects the number of samples that you can run, allows us to capture the probability of failure with much higher accuracy overall. So compromising a little bit on the mechanics gives us a much higher accuracy in terms of probability. After this, we compare the demand with the experimental distributions for the capacity, and we start doing now an element removal and progressive collapse analysis that allows us to study the failure at the local level for these towers, which is the way they go down when they do. A couple, well, I guess I will just show you briefly. This is an example of application for the Eastern Pennsylvania, where we took up the data on every single tower and every single conductor cable, their geometry, their location, and we studied the entire power network. We ran a hurricane through the region, and we studied the probability of failure of each tower, each conductor cable, each power line, and the system as a whole, and the probability of being able to preserve, to satisfy the power demand. Here I'm running out of time, so I'm skipping this. One of the interesting results is that, for instance, for this tower here, the maximum probability of failure does not coincide with the moment where the wind load is maximum, because you also have to account for the direction of the load. And over time, because of the fact that the earthquake moves and the wind field changes, the main direction of the wind changes. So we end up having the highest probability of failure when the direction is the least favorable, even if the load is not at the maximum. We did an entire power flow analysis, which with and without failures for cables. See, the case with cables is the one with the blue bars. And you see that most of the times they don't matter, but in some cases they do. And we studied this is for another example, also the entire recovery. And we were able to show, I will show just the video here, what the probability of unmet demand and how it evolves as time goes after the occurrence of the event. And you can see how this probability distribution evolves, and eventually as the time passes, the probability of having unmet demand becomes lower and lower and lower. So I just want to conclude with a couple of messages. The first one is that, as I said, what we really want to do is pre-event decision-making. And these messages also tie with what we were saying last week at the workshop. The main idea of how to use PRAISys and similar tools, in my opinion, is to run the analysis with the model in the current state, run the analysis with a model that includes a mitigation action, compare the results, and repeat for each mitigation action that you want to study. But to do this, there are two conditions. The first one is that the model has to be able to capture the effect of the mitigation action. Some mitigation actions are easy, like strengthen structures or build the redundant structures. But there are mitigation actions that are not as trivial, like change the decision policy, or purchase more mobile generator that can facilitate the recovery, or have more heavy equipment, or more crews, or stock spare parts. So all these simulators, to capture these mitigation actions, have to embed them in the models. And this is one of the things that we really strive to do in PRAISys. The second condition is that the model has to provide a portfolio of output metrics, and the decision maker has to decide how to weight them. It's not just a number. You can consider short-term or long-term resilience. You can consider monetary losses or casualties. You can focus on the expected values or on the tails of the distributions. Maybe what you want is to prevent a very unlikely but very large loss, and that's all you care about, not the mean. Or you may want to focus, for instance, on the most vulnerable segments of the population that otherwise would not be reflected in any one of the other metrics. So I think each one of these simulators have to provide a wealth of outputs, and this is, again, what we're trying to do here. Moving forward, well, PRAISys is available for download in a version that is still a sort of beta, but you can play with it. And not everything I showed is included, but there is something. We started thinking about the PRAISys 2.0 that is a real complete rewrite based on what we learned from the first attempt. And most importantly, we are trying to establish a center. Maybe I should say we have established it, but we haven't gone public. In catastrophe modeling at Lehigh, we had green light from the dean and the vice provost of research last month, I think. The main idea is that the solution of this problem cannot be found in engineering and science alone, but in a combination of engineering, science, and financial incentives that make all these mitigations action really implemented. And I see here some of the friends and colleagues in this adventure, and I'm very grateful that we built a fantastic team around this. Obviously, all the work that I presented is not mine. It's work of my students and postdocs and a lot of faculty collaborators. I want to acknowledge the support of all of these agencies, including my institution. And again, I want to thank the Center for Risk-Based Community Resilience Planning and Colorado State for hosting the seminar. If you want to learn more, there are the website. Thank you very much.
Thank you, Paul. That was fantastic. So, I'm sure we have a number of questions. So, for questions, I guess maybe we can use the hand raising feature, and I see one has gone up already. So. You can go ahead and unmute yourself and ask your question, or if you put it in the chat, I'm happy to read it as well. And I am organizing here. All right, any initial questions? I think the one thing I took from your beginning part is that you must drive very fast because you get to New York in just over an hour. So, I'll ask a question as people settle in on what they want to ask. Could you comment first? The PRAISys project, I've obviously heard a lot about it over the years as you guys were developing things and things were being published. Could you comment, like you said, okay, you've tried it on hurricanes. Could you comment on if there would be differences, say, applying it for tornadoes, or would all of the, I guess the science still, of course, lays out just fine, but would there be other challenges related to that? Simply, yeah, I'm not sure why, but would it work for tornadoes given the nature of those?
Well, I guess that the first two modules would need major reworking, right? Because the hazards that are currently in the platform that are hurricane and earthquake are more of a spread regional hazard, maybe relatively mild, but relatively uniform, even if not mild. The tornado would require us to rethink a little bit the way in which we create samples of damage, because we'll have an extremely high correlation. The second part, so the decision and planning simulation, as well as the recovery planning, maybe are easier to adapt, because once the damage occurred, the way things evolve may be relatively similar. One of the things that I couldn't discuss today, but we included in the platform, is two major classes of way in which the decision can be modeled. One is what we call optimization based, right? The idea is that we basically solve a certain optimization problem to try to capture the fact that decision makers will be rational people and they will try to do the best they can. So decisions will be made in a way that makes the recovery process as short as possible or something like that. So that's one class of, we have different algorithms, but they are somehow similar in this sense. The other class is instead what we call policy-based. This is a completely different approach, but it's what we hear from disaster managers, especially in small cities or counties. What they do is that they have a list, a predetermined list of priorities based on criticality of the various structures or functions. And after an event, what they do is they just go and check which of those things need repair. And then they just go from the top to the bottom. Even if it may seem inefficient, they just follow the protocol. And we implemented also this way of making decisions. I expect that in the case of a tornado, the latter is the most likely way, right? There will be a strict policy that needs to be followed. Chaos will not really facilitate a very rational sequence of operations. It will be a very strong sort of emergency management based on predetermined criteria.
Okay, thank you. And it looks like we do have a question here from Adam. Adam, you can unmute if you like and ask your question.
Thank you, John. Thank you very much for the presentation. It was really great. I have a question about the hazard quantization method that you presented. I'm specifically interested in what happens if I would like to match more than one intensity measure over the region. So let's say I have a large number of those. I assume it makes it more challenging to do this, but how much more challenging, and do you see any rational or practical limit of the number of intensity measures where this breaks down?
Excellent question. Thank you, Adam. So what we present as multivariate quantization, I always present it as a way to address multiple hazards, right? Here I showed wind velocity and water depth. In reality, I present it in this way because it's a little bit more flashy, and it makes it even clearer that in that case you need multiple intensity measures. But it would work exactly in the same way if you want more than one intensity measure for the same hazard. So if you have an earthquake and you want to consider the spectral acceleration at multiple periods, the same approach will work. The second part of your question was, is it practical? The answer is that it is very demanding computationally. And that's why we started going into that multi-step hazard quantization that gives us an enormous speed up. It's probably more than one order of magnitude. We haven't tested in a lot of cases. We're still, as I said, we're still working a little bit first on the mathematical proofs. I think we completed the proofs now, and we are in the process of testing it with some numbers. But I think that is making it feasible. It's always a trade-off, right? How much can functional quantization costs depends on how much the following analysis costs. So if you have a resilience analysis that takes months, which I think is credible, right? Because if these are pre-event studies, I can imagine investing into several months of calculations before making major investment on, let's say, a redundant power line. So if you have months of analysis, if functional quantization takes 2 weeks, I think it's fine to select good input for those 2-3 months of analysis. So it's a trade-off, but it is slow and demanding, and we're still working on how to make it faster.
Thank you. That makes a lot of sense. Thank you.
All right, and Jamie, I saw you had your hand up, but you pulled it. Do you not? I guess your question was answered.
Yeah, I was going to ask about some of the multi-hazard functional quantization, but I think the multiple IM essentially hit on some of the same challenges. So thank you.
Okay. Well, I have one other question. You mentioned early on about humans and decision making and things. Are you So to what your research group have you looked into that social science or human aspect, and if so, what have you done? And I know you didn't have time to present everything today, so could you just maybe touch on that?
Sure. So we did a few different things. I will touch on three. The first one is that as part of the PRAISys team, we had obviously social scientists, people who study regional planning, policy making, one economist, etc. So they always brought that component to everything we were doing. For instance, for the decision process, the decision model that I called the policy-based, they were those defining the policies, right? So they were those collecting the social, demographic, economic data and defining, for our case studies, the ranking that would be made. Another thing that we're doing right now is with a different group of scientists, this one more into anthropology and psychology, we are studying perceptions of recovery. So we have a notion, and this was pre-COVID, that the perception of recovery affects the actual recovery, because individuals and decision makers will make decisions based on how much and how fast they think everything else around them will recover. And so this can create a virtuous or vicious loop. And this is something that we have not embedded in PRAISys yet, but it's something for which we have been working a couple of years to build the models and eventually may go in there. I said three, and I forget the third one that I wanted to mention. So I guess there are going to be two.
All right. Well, we'll take one more question from Leonardo, and then I think we're Leonardo.
Thank you, Paulo. If we take your hazard quantization and remove the hazard part and just use the quantization as a tool, could be applied directly to the, let's say, resilience fields or loss fields in cases where we don't have enough data, and it becomes almost like a better way of interpolating and getting a sense of what's going on in communities.
Yes, you can. As I said, the root of the methodology was in pure math. And what we did was just generalize it a little bit to expand the range of applicability. We did publish, for instance, a paper about applying this to stochastic mechanics, where we had a plate with random material properties, and we were studying the displacements of this plate. That's a very famous benchmark in stochastic mechanics, and we used quantization for that. We used it for life cycle functions, right? Those functions that my dear friend Dan Frangopol uses to describe deterioration, etc. We tried to use functional quantization for those because we were looking for a place where they would do worse than Latin hypercube. Those are functions governed by very few parameters. And so we were thinking Latin hypercube here will do better. Turns out FQ was doing better based on all the metrics we were looking for. So yes, the methodology is quite general. If you can create a set of samples for a subsequent analysis, you can use it.
All right. Well, with that, please join me in virtually thanking Paulo for an excellent presentation, and we're glad that you were able to join us. And
thank you again for inviting me. I appreciate it.
Our pleasure. So, well, thank you, everybody. And with that, we'll go ahead and end the meeting.